Hi friends, this will be my third attempt at recording a video for the differential equations class, the notion of which is the superposition principle and solving non-homogeneous linear differential equations. So, assuming I get no interruptions, let me bring up my iPad. All right, so the superposition principle says if you've got a linear operator, right? So think about those polynomials of differential operators. And you figure out what the homogeneous solution is that corresponds to that. And then you can talk about also dealing with non-homogeneous differential equations, and the way you're going to tackle that is to find at least one solution, y sub p, for the linear differential equation, the non-homogeneous linear differential equation, and then you're going to formulate your your general solution for that, for the non-homogeneous differential equation, by adding the particular solution and the general solution to the homogeneous case. All right. So, good question to ask here would be why? So, start out with two solutions. This, by the way, is a really standard math trick. If you have two solutions to an equation, you often want to look at the difference between them and see, what difference it actually makes. So we're going to assume that we have two solutions, call them y1 and y2, for L of dy equals f of x. So if you take the difference, y1 minus y2, and plug it in with that differential operator, because differential operators are nice, you're able to distribute across that y1 minus y2. And because they're both solutions to the non-homogeneous equation, you get f of x minus f of x, which means you get 0. And that means that your y1 minus y2 is a solution to the L of dy equals 0. So because that is a solution, then by going back and choosing different y1s and y2s, you could have lots of different solutions. In fact, if you look at all the possibilities, that would be the general solution to the homogeneous equation. So if you can find just one solution to the non-homogeneous differential equation, then you can find them all. So might be good to see a quickie example on that. And so I'm just going to look at y double prime minus y equal x. The homogeneous solution, you can do that pretty easily. I've skipped over the steps, but then looking at it, it's going to turn out that the y sub p is going to be minus x. If you don't believe that, we can go back and plug in, and we'll have to find the derivative and then the second derivative in order to get there. And once we calculate the second derivative, then we can plug in for that left-hand side. That's what I mean by hitting it with the differential operator. And that is going to give you your y double prime here and your y here. And so with regard to those, if you notice, we have an a e to the x in the first part minus an a e to the x in the second part, and a b e to the minus x and minus a b e to the minus x. And so it all worked out super conveniently, probably seems contrived. That's because I got a problem that actually worked out before I started. But the minus of a minus that we see here, then those bits are actually going to go together so that you end up with sorry, those will go together so that you end up with just an x there. So it is actually a solution for any choice that you make there. All right. So let's take a look then at, okay, now let me stop for a second and say this. If you can guess what that one of those y sub p's are, you are in luck. Unfortunately, guessing seems like it's a very hard way to go at stuff. If you're a wizard and you've got your magic wand and you can wave it around, maybe that does something for you. So get out the sorting hats. We're going to go to wizarding school, and I'm actually going to show you how to magically guess the answers. Sounds silly, but it's kind of what we're doing here. So going back to the iPad again. And oops. And we want to look at method of undetermined coefficients. Okay. So the method of undetermined coefficients is how to guess your y sub p. That's what it's about. So I make mention right here that there's another name for this. It's also referred to as the method of annihilators. It seems though that I'm the only person in the universe who's ever heard that term. So let me explain as we go along, and hopefully it will make sense and I won't just look like I'm saying crazy stuff to you. Well, no more so than usual. So what we're going to start out here is a non-homogeneous differential equation, but we need for it to be linear, okay? And so if it's linear, at least some linear equations, we know how to figure out what the homogeneous solutions are, right? So what you have to do is to look at the homogeneous equation, get that y sub h, and then look at f of t, the non-homogeneous term. Do they look alike? If they don't look alike, life is wonderful, okay? This ends up being pretty easy to do then. So quick example to show what sort of things can happen there. So down here, the example we've got has a has y double prime plus y is equal to t squared. So that y sub h, y'all should be able to do, maybe not in your head, but you'll have the r squared plus 1 equals 0. R is plus or minus I. And once you get something that's imaginary, that tells you to use sines and cosines. On the other hand, our f of t that we've got sitting over here is a polynomial. Now, the r for your sines and cosines was plus or minus I, okay? And the polynomial, if it had been a part of the y sub h, it would have to come from r equals 0, okay? So the t squared, a polynomial, is fundamentally different than the trig functions, the sine and cosine. They come from different roots of the initial equation. So once we get to that point of it, though, what we say is, I need to get t squared as my final answer. But I could have anything over here on my left-hand side. So I know that I'm going to take derivatives, but I'm not going to take any integrals. So I don't think that I should have any degree that is higher than the t squared that appears there. And so I guess that it's going to be at squared plus bt plus c. And if you're saying, well, now how do you find out what the a and b and c are? That is the rest of the trick. And we'll come upon that here in a minute. Okay. Another quick example. Here we've got the y double prime y double prime minus y instead. And so that's going to get you a homogeneous solution of c1 e to the t plus c2 e to the minus t, okay? And then because we have a 3 cosine t over here, that tells us we don't have an exponential function in our f of t. So in trying to figure out what we want for our y sub p, we make the guess that we might want cosines and we might want sines, all right? But they need to have the same frequency to them, right? Since it said cosine t, you don't jump over to using sine of 2t. But because when you take derivatives of sines and cosines, they might go together some way or another, then we just set those up, okay? So we're just taking for our y sub p and trying to be one step more general than what you've got in your f of t, right? Now, on the other hand, if your f of t contains anything that shares roots of the initial equation, so then your y sub p is going to take the generalized form of the f of t like it did before, but then multiplied by t to the m, where m is the multiplicity of that root, okay? So taking a look here at some examples will help us see what's going on. So here we've got y double prime plus y is equal to t. So if you look at your roots for that, you're going to get your r equal to -1 and your r equal to 0. So r equal to -1 gives you the c1 e to the minus t, and the r equal to 0 gets you just the constant of 1. That's the e to the 0t, okay? But because of the fact that we have a t in there, in our f of t, and those share a root, you know, they're connected together, they're the same kind of equation, same kind of function, then you would say to yourself, okay, I need to think about that t to the first, and I should back up on this a little bit here. Let me fix this a little. So I should think about, first of all, if I'm going to have a t, then I need to have at plus b, right? So the general first order, or first degree polynomial. And then, because that root, r equals 0, had a multiplicity of 1, then I'm going to multiply by t to the first. And so I end up with at squared plus bt, okay? So that's how we're guessing our solutions. So let's take a look at this one down here. It's got y double prime minus 9y equals t e to the 3t. So when you get your homogeneous solution here, you're going to have a c1 e to the 3t and a c2 e to the minus 3t. So because t e to the 3t and e to the 3t shared the same root, then they're going to have to actually be considered together. So because I have t e to the 3t, I have to think then about at e to the 3t, and then plus b e to the 3t. So go all the way down to the constant term times the e to the 3t. But because my root that appeared here, my r equals 3, that's supposed to say r equals minus 3, isn't it? Nope, it's supposed to say r equals 3. Sorry, my bad. Because my r equals 3 is multiplicity 1 for the homogeneous part, then that says that I need to come down here and multiply by t to the first power, okay? So that means that my y sub p that I'm guessing, remember I'm still doing a guess, is going to be this at squared plus, I'm sorry, at squared e to the 3t plus bt e to the 3t, okay? So the short of it is that you have to look at what kind of things that you can get. If you get zeros for your roots, that's polynomials. If you get real numbers for your roots, then you've got exponentials. If you get complex numbers for your root, you get an exponential times a sine or cosine, right? So you only have to worry about jumping it up a power if the roots exactly correspond, okay? And the reason behind this is that if you took your L of dy equals f of t, and you figured out the annihilator for that f of t, and you applied that to both sides of the equation, then you'd have the annihilator times L of d times y equals 0, because you annihilated the stuff over on the right-hand side. So that says that the solutions that you're looking for in this y sub p are the ones that appear in the solution to that higher degree equation, and not the ones in the lower degree equation, because the ones in the lower degree equation come from the homogeneous part, right? So, you know what would be really good to do? Actually work out an example. So let's share screen again and jump over here to the iPad. And we are going to look at, is this, yeah, this is my example number 1. By the way, somebody asked in the questions the other day, could I work these out instead of having them worked out ahead of time? Unfortunately, I didn't get that suggestion until I'd already done this particular one here. So this particular video, I already have the solutions worked out. I will try to incorporate that into future stuff that we're doing. But if we take a look at this non-homogeneous differential equation we've got here, we see that the left-hand side there is going to have an indicial equation that looks like r squared minus r minus 2 equals 0, okay? And that's something we can factor nicely, and the solutions, I shouldn't say solutions, the roots of the polynomial are r equals 2 and r equals minus 1. And once we know that, then we can see that the y sub h is just going to be c1 e to the 2t plus c2 e to the minus t. So it's actually relatively easy to get our homogeneous solution there. Now, the y sub p over here, we're going to take a look, and that one, we don't see it having anything to do with the y sub h, right? So we're going to say that that y sub p is just a e to the 3t, and then because our differential equation has 2 derivatives in it, we're going to take those derivatives, get 3a e to the 3t and 9a e to the 3t, and then we're just going to plug back into the left-hand side. So just replace the y double prime and the y prime and the y with those expressions that we just got through getting for them. And when you do that, it'll all simplify down to having 4a e to the 3t. And you needed it to be equal to 8 e to the 3t. So that means that when you cancel off the e to the 3t's, your a had to be 2. So your y sub p that we were looking for has to be 2 e to the 3t. Once we've got that, we can just walk right over here, put it in on our y of t, and add in our y sub h that we had before, and we've got the general solution. So that's actually pretty cool. So so the main trick there was simply spotting that we didn't share any roots between the y sub h and the f of t. Once you know that, then you can just say, okay, my f of t looks like this. In this case, it was an e to the 3t, so it's going to be some multiple of e to the 3t. Because when you take derivatives and multiply by constants and add and subtract, e to the 3t doesn't change. So it's going to have to be made by something times e to the 3t. It's just a matter of figuring out what. So that might be a little bit underwhelming, I guess. But let's take a look at another one here, and with this, we'll have a little bit more work to do. All right, so we've got y double prime minus y minus, I'm sorry, y double prime minus y prime minus 2y equals 4t squared. So y sub h is pretty straightforward to get. You'll set up and have r squared minus r minus 2, factor it, solve, and you end up with r equal 2 and r equals minus 1. And that gets us the y sub h. Then we're going to come back through here and say our y sub p, because we've got a 4t squared over there in our f of t, our y sub p at worst will be a polynomial, okay? And then you just go through real quick with getting your derivatives. And once you've got your derivatives, you plug them in on that left-hand side stuff. Yp double prime minus yp prime minus 2yp. And that's not real bad to actually do, but we have to group the things together, all right? So I am going to try to group all of the t squares together, but there's only one of those t squares, right? And then I'm going to group all of the linear t's together and have the minus 2a minus 2bt. And then finally, I'm going to group all of the constants that are left together, right? Now, this is actually a technique that you should have seen before in Calc 2. It's referred to as equating coefficients. Since we know that minus 2at squared needs to turn out to be 4t squared, then that minus 2a has to be equal to 4. If you have two polynomials that are equal to each other, then they have to be equal for all t values, which ends up meaning they have to have the same coefficients. So you equate coefficients there and find out that your a had to be minus 2. And once you know that your a is minus 2, you plug it back into the minus 2a minus 2b equals 0. And since that's the case, then you've actually got, what is it? Minus 2 times minus 2 is 4. And then minus 2b equals 0. And so you solve for b and find out that the b had to be positive 2. And then once you know both a and b, you can stick those into the equation that has a and b and c in it and solve for c, and the c had to be 4. So once you get to that point of things, you can come back and set out your general solution by saying, I need to have that for my y sub p, and then I'm going to add my y sub h that I figured out earlier, and then I've got my solution. So now I didn't quite finish this one, so let's see what else is going to be involved in it here. No, I don't need a keyboard. Thank you for trying to help, iPad. Okay, so I'm going to have to figure out what y of 0 is. Oh, since I know y of t, I need to first say something about what's y prime of t, because we're going to have to plug in. Y prime of t is minus 4t plus 2 plus 2c1 e to the 2t minus c2 e to the minus t. Okay, so y of 0 is going to be, what was that? 4 plus c1 plus c2. And what did we say that was equal to? 1. Okay. And y prime of 0 is then going to be 2 plus 2c2, and then minus c2. I said 2 twice there, didn't I? All right. So let me back up and say 2c1 and minus c2, and that's supposed to be equal to negative 1 at the end. So rewriting these, I have c1 plus c2 equals 1, 2c2 minus, I did it again. 2c1 minus c2 equals negative 1, right? And if you want to do substitution, have a field day, but I'm going to get finished faster because I'm going to add those together and have 3c1 needs to be equal to 0. c1 has to be 0. And that being the case, then c2 needs to be 1, since it has to be plugged into either of those equations. So now our final solution here is going to be minus 2t squared plus 2t plus 4, and then plus 0 e to the 2t. Well, heck, I might as well just knock that out. And then plus 1 times e to the minus t. All right. So we can get solutions to these. We can get solutions to these initial value problems after we get the y sub h. So then we need to look at an example or two where we have something with the shared roots, because those are going to be the hard ones. All right, let me pause for a second here. Okay, I'm back. So for examples of these that have the shared roots, let's try to look at one that's not too cumbersome, but that gets the idea of what kinds of stuff we have to do, right? So we've got y double prime minus y prime equals 2t minus 3. So if you are doing the homogeneous part of it, then you'd be thinking about this here. And for that, you'd have r squared minus r equals 0, because you're guessing that you're getting y equals e to the rt. So that factors into r and r minus 1. So that means that you're getting your general solution here to be c1 times e to the 0t and plus c2 e to the 1t. Now, e to the 0t is just going to be a constant value of 1. So I'm just going to write that down. Okay. Now, then we're going to come over here and look at this, our f of t. And we know that constants and polynomials in general come from having an r value of 0. So that says that when we start looking for our y sub p on this, that we are going to start out with that general form, a, oh, I guess there's no need to put a capital A, at plus b, all right? But because of the fact that we had the r equals 0 happening with multiplicity 1 there, we'll say times a t. And so we have at squared plus bt as just our general form. But we can quickly figure out yp prime 2at plus b, yp double prime is just 2a, and so our yp double prime minus yp prime, we're just plugging in here 2a minus 2at plus b, and that's going to be then minus 2at plus 2a minus b. All right, I just separated them off in the powers and grouped them. And what was that supposed to be equal to? It was supposed to be equal to 2t minus 3. I guess that might have been nicer to write over here. But this minus 2a and that 2 have to be equal. And this 2a minus b needs to be equal to, needs to be equal to the minus 3. Since the minus 2a is equal to 2, a has to be minus 1. So 2 times minus 1 minus b needs to be minus 3. So that says that minus b needs to be minus 1. So b is equal to 1. So our y sub p is going to turn out to be minus, I lost my place, minus t squared plus 1t. Okay. And then putting things together, our general solution is minus t squared plus t, and then plus, going back up there, c1 plus c2 e to the t. And if we had an initial value problem, at this point, we would be plugging back in order to solve for what the c1 and the c2 needed to be. So I keep kind of looking at the camera and shrugging because it's all very doable, but you need to keep in mind that it's doable in part because I've done these before, all right? As you're doing them, you may run into some little problems. And something that I would suggest for you to do, I never did this when I was a student, and I was always told that I should, check your answers. There's no need to ever get an answer wrong. You can always go back and plug these solutions into the differential equation and see if you get it. So, okay, let's do one more of these, and then I think I'll call it a day. So this one, okay, that seems to have caused a problem. Let me try it again. So AirPlay, screen mirroring. this is going to be one of those times that I wish that I could edit better. Let me pause again. And I'm back. Okay, so I'm having a little bit of problem with the iPad. Hopefully I can use a cable to connect with it. Yes, turns out I can. All right. So we're going to go over here to my undetermined coefficients example 4. And this time we've got a y double prime plus 2y prime plus 2y equals e to the minus t sine t. So again, if you were doing the homogeneous portion, you'd end up with an r squared plus 2r plus 2 that you're setting equal to 0. If you want to, you could go ahead and just use the quadratic formula on this, but I find that being able to spot what's going on with completing the square actually is a little bit of an advantage. Okay, so once you've got those two roots, then that tells you that your y sub h is going to be a e to the minus t cosine t plus b e to the minus t sine t, right? Okay, oh no, that is of the same form, right? So those are sharing a root. So what that says for you is that that you're going to need to, on this, jump everything up by 1, okay? So our y sub p, we would normally come in here and say, I want it to be just a e to the minus t cosine t plus b e to the minus t sine t. But of course, that can't be the solution because of the fact that that is exactly the form that we have for a homogeneous solution. And so when we plug it back in, we'll get 0. However, if we multiply it by a t, because we have the multiplicity of 1 of each of those roots there, then we should be able to get at e to the minus t cosine t plus bt e to the minus t sine t. Okay, that looks pretty messy. Okay, and things are only going to get worse because we're about to go yp prime. And so when you take the derivative of that t e to the minus t cosine t, what you'll have happen is that you'll use a product rule, and you're just going to go through on each one of those things one at a time. So 1 e to the minus t cosine t plus t times minus e to the minus t cosine t plus, my God, this is a mess. Okay, plus t e to the minus t derivative of cosine is minus sine t. Okay, plus b times, and we do the same thing with the sine. The 1 e to the minus t sine t plus t minus e to the minus t sine t and plus t e to the minus t cosine t. Okay, so and here's a tip that I wish that students would listen to more. Don't just make it worse and worse as you go along. Every time you do a step like this, tidy up. Okay, that sounds like the old OCD guy trying to advise people to all be neat and tidy, but it's just to make things a little bit less miserable. So minus t e to the minus t sine t plus b times e to the minus t sine t minus t e to the minus t sine t, and then plus t e to the minus t cosine t. All right. So I said tidy up, but let's take a notice here of a little something that went on as we went. Okay. So notice that we have some cross-term things going on. So I might suggest on this to go ahead and write a e to the minus t cosine t, and then plus, and I'm going to put some parentheses there, t e to the minus t cosine t. All right. So if you notice, you had a minus a coming out of that first one, and then you'll have a plus b coming out of the second one. All right. Then we will also end up having a plus b e to the minus t sine t, and plus, I'm going to put parentheses and have a t e to the minus t sine t. And so from that, I have a minus a on the first one, and I have a minus b on the second one. Okay. Now we're going to do it again. So bear with me as we try to finish this out. So I have an a times this minus e to the minus t cosine t, and then a plus e to the minus t, and the derivative of cosine is minus sine. So I'm going to want to tidy that part up as we go along here. And then plus quantity minus a plus b, t e to the minus t cosine t. Nope. We have to take the derivative of that. So since what we have to take the derivative of is t e to the t cosine t, what we're going to have to spot is that we have done that previously. So I am going to just copy this stuff up here. And so I'll have e to the minus t cosine t minus t e to the minus t cosine t minus t e to the minus t sine t. What a mess. All right. Plus, what was the next part we're taking derivative of here? The next part is this b e to the minus t sine t. So we'll have a b times minus e to the minus t sine t plus e to the minus t, and the derivative of sine is cosine t. Okay. Plus minus a minus b times, now we have to take the derivative of the t e to the minus t sine t, and that is what we did right here. So we're going to copy that down, e to the minus t sine t minus t e to the minus t sine t plus t e to the minus t cosine t. All right, that the technical term for that is a god-awful mess. So what we're going to do is to collect together all of our stuff with just plain with just plain e to the minus t cosine t on it. And then plus, then we're going to collect together all of our stuff that has e to the minus t sine t on it. Plus, then we're going to collect together everything that has a t e to the minus t cosine t. And finally, all the stuff that has a t e to the minus t sine t. Okay, so let's start then with the e to the minus t cosine t stuff. So we can spot up here that will have a minus a on it. And then here, we're going to end up with another minus a and a plus b. And then here, we'll have a plus b. And then from, oh, that's got it, doesn't it? I thought sure we had another of those terms there somewhere. Okay, and so, all right, then we're going to worry about the e to the minus t sine t. So e to the minus t sine t appears here and here and here. Okay. And so we will end up with a minus a from the first one and a plus b. Nope, that's wrong. A minus b from the second one, and then a minus b on that one. Gosh. All right, then we're going to look for the t e to the minus t cosine t. And we can see that there and there. Okay, so that should seem like it's not so bad. So since it was a minus here, we will have an a minus b. And since it's a plus here, we'll have a minus a minus b. All right, then we will look for the t e to the minus t sine t. We see it appears here and here. Okay. And so, since it is a minus here, sorry, I need to do things in order. Since it is a minus here, then we end up with a minus minus a, and then a minus b. And then because it's negative here as well, it'll cancel out the two signs on that, and we'll have that. Oh, Lord, which is equal to minus 2a plus 2b e to the minus t cosine t plus minus 2a minus 2b e to the minus t sine t plus quantity. Those cancel, minus 2b t e to the minus t cosine t. And those cancel, and plus 2a t e to the minus t sine t. All right, so horror of horrors. Now we have to scroll all the way up here and remember what to plug into. So y double prime plus 2y prime plus 2y. So okay. So I'm going to copy down the y double prime one first because it is kind of a pain. Minus 2a plus 2b cosine, nope. E to the minus t cosine t plus negative 2a minus 2b e to the minus t sine t plus, I'm sorry, that should have said minus 2b t e to the minus t cosine t plus 2a t e to the minus t sine t. All right. Now we've got to have plus 2 times this. So, fortunately, the e to the t cosine t, so plus 2a e to the minus t cosine t, and the b e to the minus t sine t, those are relatively easy to remember, plus, this is for the t e to the minus t cosine t, so minus a plus b. So minus 2a plus 2b t e to the minus t cosine t plus, now we have to do 2 times the sine one. So that's going to be a minus 2a and a minus 2b. T e to the minus t sine t plus, now 2 times the original. I have, honest to God, forgotten what it is now. The original was just a t e to the minus t cosine t to b t e to the minus t cosine t. All right, so ready to collect all these things together? Stuff times e to the minus t cosine t plus stuff e to the minus t sine t plus stuff t e to the minus t cosine t plus stuff t e to the minus t sine t. And we just have to do bookkeeping at this point. So let me take advantage of being able to draw in color here. Let's get the e to the minus t cosine t stuff together. And it appears here and here and nowhere else. All right. So that means that we can put those together. And when we do, notice that we have a minus 2a and a plus 2a. So we end up with just 2b. And here for the e to the minus t sine t, we're going to have that here and here. And that means that we will have the 2b and the minus 2b cancel out and have minus 2a. That might be nice. And then we're going to get the t e to the minus t cosine t part. So that's here and here and here. So with regard to that, we will have minus 2b This is starting to run together a little bit. I'm just going to write it down. Minus 2b minus 2a plus 2b and plus 2a. Oh my gosh, check that out. B's cancel, A's cancel. All right. Now we need to do the ones for the t e to the minus t sine t. And I am noticing that I had a typo way back here that is easily detectable because of the way we did our bookkeeping. All right. So we are finally getting the t e to the minus t sine t, and we can see that that appears here and here and here. And so when we put those together, we have a 2a, a minus 2a minus 2b, and then a plus 2b. And they all cancel out. So that means that we end up with 2b e to the minus t cosine t minus 2a e to the minus t sine t. And what was that supposed to be equal to? Going all the way up to the top, it's supposed to be equal to e to the minus t sine t. E to the minus t sine t. And no e to the minus t cosine t's. And so that tells us that when we equate terms here, minus 2a has to be equal to positive 1. A is minus 1/2. The y sub p we did all this effort to get is minus 1/2 times, which ones did the a go with? Oh, a went with the cosine. T e to the minus t cosine t. And our general solution then is going to be minus 1/2 t e to the minus t cosine t plus a. Now we were writing it with a C1, weren't we? C1 e to the minus t cosine t plus C2 e to the minus t sine t. Okay, so the bad news is that's a horrifying mess. The good news is it will be very, very rare for you to get one that is that much of a mess, okay? I try to work out a problem or two that are challenging for y'all. I underestimated that one, okay? But I didn't want to chicken out of it and make y'all think, oh, we can just give up all the time. They work out. Sometimes it takes a lot of effort, but they work out, okay? So essential things then is that your method of undetermined coefficients gives you a way to guess the solution. But your guesses, you put the A and the B into it, and you solve for what the A and the B are, because they have to turn out to be something to make the non-homogeneous term turn out to be what it is. So take a deep breath, jump in on it. You can totally do this. You got it.